So I will talk about the research of myself and my team, and try to make effort to move toward robots and related stuff. First, to clarify what we consider as AI is very different from the mainstream AI, where the mainstream is basically intelligence is a collection of problem-specific and domain-specific functions. We, in recent years, we begin to use the phrase of AGI for artificial general intelligence. The basic attitude is to take intelligence as one whole piece, which should be considered entirely. Under that name, of course, there's still different approach, okay, even though they're all called AGI. Clearly, I can only talk about some of them. One thing is how to, even if we agree that we want a general purpose system, how to build it, still we have very different opinion and approach. So I use 3 pictures to show you intuitively what they are. The first one is what I call hybrid. This is typically the opinion of the mainstream AI people who kind of like still interested in AGI. Their attitude will be, it's kind of like, you see, if you check the current faculty researchers doing AI, and that's typically the case that it's kind of like you do vision, I do robotics, the other guy doing natural language, and so on. Eventually, we put them all together into a general purpose system. That's what I call a hybrid approach. And this approach sounds intuitive, but many people, especially the people currently in the AGI field, doesn't think it's going to work. The major reason is because all those blocks are built according to very different fundamental assumptions and the technique. They just simply doesn't work together. So for the AGI team or the field, most people is taking the approach in the middle. That is, you can still have a modular architecture, but you need to have an architecture in the first place. That is, you need to have a blueprint for the whole system. Then you begin to talk about who is doing which part, according to that overall design. So that's kind of like the majority in the current AGI field. And finally, there is a third one, which is more extreme. It happened to be the one that I have been pursuing, which I call it a unified approach. This approach basically takes the position that intelligence is basically one thing. You see different letters in this picture is because you're observing it from different angle and different perspective. And also use Professor Chera's previous metaphor, you're seeing it from different distance. That's also, I see that. So clearly this one sounds more radical. Unified, according to what? Okay. So clearly intelligence is such a complicated thing. No one can actually try to solve it with, say, a few lines of code. But my position is still I want to start from a different working principle or working definition of intelligence. So this is the first paragraph is my definition of intelligence, which see intelligence as the capability of a system to adapt to its environment and work with insufficient knowledge and resource. So in this definition, actually there are 2 points. One point is adaptive. Another one is the restriction of insufficient knowledge and resource. I will start with the second part first because that's the most special one in my definition. That's a so-called assumption of insufficient knowledge and resource, or AIKR in our papers, because it's mentioned so many times, so we cannot use this long phrase all the time. What that actually means? It means 3 points. One point is the assumption or your design have to depend on a finite processing capacity. Okay? You cannot assume you have infinite amount of space or time or computation power, okay? Which sounds like common sense, but if you check theoretical models, including the Turing machine, okay, they assume infinite amount of things. Second point, to me, a truly intelligent system has to work in real time. And this is relatively easier to be upgraded by people working in robotics because all robots work in real time. But the many people doing other part of AI, they don't care about real time. But to me, that's crucial. And finally, is to be able to open to novel or unexpected tasks. It cannot be designed to just do a certain number of things, and then whenever you get something novel, it will just simply die. So that's my assumption about what I call insufficient knowledge and resource, or put it in another word is the system have to always assume it doesn't know everything, and everything it thinks it knows, it can be wrong, and also it doesn't have the time to try all possibilities. Okay, if that's the hard restriction you put into the system in the first place, then under that condition, what can you do? One thing is pretty clear, under this assumption, there is no way for the system to be perfectly correct or optimal. It's just because, that's actually implied by this assumption. If you can always be perfect, then you must know everything in advance already. So the solution is, of course, adaptation. That's the word that have been used in AI a lot, but accurately speaking, what does it mean? To me, it means the following things. Two things with respect to knowledge. You don't know the future, or I don't think anyone really knows the future. What you know is the past, but you have to use the past to predict the future. You have no other source. Okay? But you know the past and the future will be different. Okay? So that's the dilemma we're facing. And this is with respect to knowledge. With respect to resources, you never have enough time. So that what you do, you always have more demand than what you can afford. Okay? So the solution, of course, is try to use your current available resource in the most efficient way possible, which is directly related to the concept of attention, resource allocation, and so on. And finally, by adaptive system, we mean a system try to adapt. It doesn't mean it will always adapt successfully. That's something you don't have. So that's basically the philosophy guiding my research. How to turn this philosophy into a concrete AI design. And also, that I mentioned, I want to use a unified approach, meaning I use basically a single technique to do the whole thing. And what's that technique? The one I take is the reasoning system framework. By reasoning framework, reasoning system, we mean the following. Well, this part is not controversial. This is not my definition. That's the Euro definition. Okay. For a reasoning system, you need to have a knowledge representation language or a formal language. And you need to have a semantics, which talk about define the truth and the meaning in that language. And you need to have a set of formal inference rules. So these three components typically is called a logic. Then when you want to implement it into a computer system, you need two more at least. You need some kind of memory structure, and you need a control mechanism to decide at any moment what to do next. Okay. So that's what we do. So the system we have been building is called the non-axiomatic reasoning system, or NARS. That is, on one hand, it is a reasoning system according to the previous slide. On the other hand, it's fully based on the assumption of insufficient knowledge and resource. Some people will think that is a contradiction, which sounds like a contradiction, because the traditional reasoning system basically is axiomatic in the sense that inference is theorem proving. You're given a bunch of axioms, which is a given truth. Then you do some inference, you get derived truth. That's what you call theorems. Okay? So I named this one non-axiomatic reasoning system just to make it clear. In the system, there is nothing absolutely true in the sense that it can be taken as axiom. So that's basically what my philosophical assumption asked me to do. So as a consequence, you can guess, this system is actually fundamentally different from the traditional reasoning system out there in all major aspects. So we just mentioned the basic. Let's start from semantics. So this is the traditional view. technically is called model theoretic semantics. In philosophy, it's sometimes also called the correspondence theory of truth. Even if you don't know any of those fancy names, you know the idea. Okay, that's the intuitive idea. So the meaning of a symbol in your mind is an object in the world, okay, which it refers to. Okay, so what is flower in my mind? That flower is that really the real thing in the world, and also the relationship in your mind corresponds to a relationship between the world, the object in the world. So if what you said match the reality, what you said is true. Okay, if it doesn't match, it's false. That's common sense. So this to me is a pretty good approximation, but according to my philosophical assumption, I'm not taking this one, accept this one anymore. Instead, I develop a new semantics which I call experience-grounded semantics, which is kind of like this picture. It does not assume a predetermined partition of the world into objects and the relations which you only need to put label on. Instead, the partition is actually formed within your mind. The world, of course, exists as a whole, okay? But each individual actually identified in your mind. And so also now you'll see that the concept, the meaning of a concept, like what is a flower, is not that thing in the world anymore. Instead, it's its relations with the other stuff in your mind, how they're related to other concepts, and also to mental image and to vision, to a whole bunch of others. And also truth. There is no absolute truth anymore because you cannot directly compare your mind, the content of your mind with the outside world. What you can do is to compare your mind with available evidence, which is also part of your experience. That's why it's called experience-grounded semantics. So if experience change, the meaning of concept in the system change accordingly, and also the truth value you give to statements also change accordingly. So that's the basic idea. So here are some technical stuff. What's the language, the formal language I use? I use something called term-oriented language, which is fundamentally different from the popular one that everyone is using, that's first-order predicate coders. In this term-oriented language, the basic concept is a term. A term in this context is nothing but an identifier or name of a concept within the system. Okay. To make things simple, I just use English words, but actually a term is not necessarily a word. It's just an internal ID. And the basic statement is a subject term, a predicate term related by a copula. Like this is a subject, this is a predicate, and this is a copula. And the intuitive meaning of this copula, what I call inheritance, is that the subject is a special case of the predicate. Just like in this example, water is a type of liquid. And this copula has the following basic feature or property. It's in its idealized form is reflective and also is transitive. If A is a type of B, B is a type of C, then A is a type of C. Then what is the truth value? Well, as I said, everything in the system will be true to a degree, so you can guess. I'm going to use a multi-valued logic. But I'm actually going even further. It's not only multi-valued, it's also numerical. Not only is numerical, I use two numbers. So that makes it different from the other numerical valued system like probabilistic logic or fuzzy logic. But even those still share some similarity. There's the two components in this truth value. The first one is called frequency. The second one is called confidence. Frequency is a proportion of positive evidence among all evidence. So intuitively, it's very similar to probability. But mathematically, probability is this ratio take a limit. But in my system, you cannot take limit because that's the future, you don't know. Okay? You just know what you know at the moment. So this is relative frequency of positive evidence at the current moment. The second one is more novel. It's called confidence. This one is a proportion of evidence you have at the moment compared to evidence you are going to have in near future. Here, the near future is captured by what if you get one more piece of evidence. Compared to that, how much do you have as a ratio? So this one, clearly you can see that is an increasing function of the available knowledge. So if we assume knowledge is kind of like evidence can be measured with some kind of unit, and also it's a discrete value. So you'll see that when W equal to 0, confidence is 0. When W equal to 1, confidence is 1 out of 2, then it's 2 out of 3, 3 out of 4, it's increasing, but it will never be 1. Here, 1 actually means absolute truth. So you see that's this is a technical definition of what I call non-axiomatic logic. This is never absolutely certain. But there is a degree, some knowledge or belief are more certain than some other based on how much you know. So that's another key point. Then what? Then we can have a whole bunch of inference rules. So each inference rule take a pair of premises, which each of them take the form I just introduced, and then it derive a conclusion. And here you can also see that that's another aspect that actually, formally speaking, this logic is much similar to Aristotle's syllogistic than to first order predicate calculus, because every rule is a syllogistic rule. You have two premises share a common term, then you get a third one between the other two. Of course, now it's not Aristotle in the sense that Aristotle is still abandoning deductive logic. My system, of course, is not. So everything is true to a degree, as you can see in this example. And I have a truth value function to calculate the truth value of the conclusion from that of the premise, which I have explained in my book, but I'm not going to repeat that. So you can see this simple example. If you know bird is a type of animal and robin is a type of bird, and you derive the conclusion that robin is a type of animal, this one means 100% positive. You don't have a negative evidence here. And this 0.9 means, believe it to a certain level. And the conclusion you see is a little bit lower than that, just because it's derived. So this is the graphical representation about this rule. You see it's basically the transitivity of the corpus. It just now become a matter of degree. So this one is a little bit trivial. There's nothing special. The most representative rule is this one, is induction. Okay, how does the system do induction? Let's see the example here. If you know swan is a type of bird, well, here we're using the default truth value, which is 1 means, positive, 0.9 means you believe it to a certain degree. If you know swan is a type of bird, you know swan can swim, can you say birds swim in general? Well, that's, if I put it in this way, that's a typical so-called logical fallacy. If you read every logic book, it will tell you that's wrong. Okay? That's clearly wrong, because what you're seeing is one single instance of a bird. Okay? But your conclusion is about a bird in general. But in my logic, it's right. It's right to a certain degree. Because the existence of swan actually provides positive evidence for the conclusion to be accepted. You see here, I'm not saying it is truth. I say I have reason to believe it, and to that level of degree, according to my semantics. So we have another one which is symmetric to induction, which is called abduction. Here you see that. This is also syllogistic, but the common term appear in different positions, so they correspond to different types. So here is another example. If you know that seabirds usually can swim, and you know gull can swim, and you know nothing else about them, that's the only knowledge you have. Can you believe gull is a type of seabird? According to deductive logic, you cannot say that. Okay? But according to this logic, yes, you can believe it to a degree. because what you know indeed provide positive evidence for the conclusion. So again, I'm not going to go into the detail, just show you the basic idea. So the difference between deductive logic, deductive reasoning and non-deductive reasoning is still there in NARS, but it's no longer in the traditional sense. It's deductive reasoning can usually give you a strong conclusion in the sense that you have a high confidence. Inductive and abductive, on the other hand, each individual piece only give you a little bit of confidence. Then how to get more confidence? You merge them. Okay. So we have a revision rule here. You see that if you know the same thing from different source to different degree, and you can put them together, here the truth value is basically, say, the amount of evidence can be added together. Okay. Then what you get is a summarized conclusion where the frequency is typically a compromise of the premise, and the confidence actually is higher than either of them. Okay. So this is how the system put different evidence together, and also how it handles contradictions. If you have different opinion, like in this case, and who is winning? Well, you get a compromise, but one may be stronger than the other with respect to the conclusion. If you check the numbers carefully, you will see this is also statistics. So what basically all the numbers actually indicate, according to my formula, you have two positive evidence, one negative evidence. Then to a degree the conclusion is true, well, it's 2 out of 3. Okay, that's a frequency. But this is very different from the, say, statistical reasoning, especially the one currently used in machine learning. What we have here is an incremental revision. So each piece of evidence is going to be taken by itself. And then if you have multiple pieces, then you incrementally merge them together. Okay. So now the memory structure, you can see that each of them, let's see the picture first, and then come back. So the memory is nothing but a big concept network. We have already seen that each concept is identified by a term which corresponds to a node. And each statement is a relationship between them with a certain value attached to it, indicate kind of its strength. Okay, now it's called the truth value. But here you see that there are two types of links. That is what I call a task and a belief. That's the difference. Both of them are relations in the system. A task is something the system is currently working on. It's actively under processing. There are two types in this stage. You can tell the system a piece of new knowledge or become a task. The system not just merely put it in and also think about it. Another type is a question. Of course, that's a task the system need to process, so to find the answer. So that's what we have here. So this is a question. I'm asking the system whether Robin is a type of slimmer or not. Okay, so that the truth value is unknown. This, on the other hand, is a piece of new knowledge. I told the system that I tell you that the swan is a type of bird, and the system take it in and also begin to think about it. In this context, means that if I combine this with what I already have, what I can derive, and the white links, that's what I call belief. That's the knowledge already absorbed into the system's memory. So that's relatively kind of like a background knowledge which stay there. But again, each of them is true to a degree. And finally here, you'll see this is a bird, which is a term which labels a node, and a node corresponds to a concept, and the meaning of the concept, you see, is nothing but its current relation with the other concepts. That's what bird means to this system at this moment. So that's basically what we have in the memory. Another thing is the memory is fully prioritized, which I don't have in this picture because otherwise it's too complicated. It's just that you can intuitively think that every node has a priority value attached. It's kind of like activation level, like in neural network. Also, every link has a priority value attached. Later we will see why there is.